Let's explore the subject of parsing at a high level. Parsing is this idea that given an input string and a grammar, we want to have a process to derive the structure of our input based on that grammar. We're going to explore parsing in the context of this made up, hypothetical, very simple language. And this very simple language is going to have lexemes that are only one character long. So this is going to allow us to focus on the problems of parsing rather than scanning and tokenization. So let's remind ourselves of the rules of a context-free grammar and what we're looking at here. Well, these are 3 production rules, right? So each of these production rules is describing what is it that makes up some non-terminal symbol. So these are my non-terminal definitions. And these are the actual production rules. What is it that is a node? Well, a node can either be a char or a pair, right? So if we looked at, well, what is a char? Well, a char is going to be described as any character that is not and then what we're going to use to represent our terminals are characters surrounded in single quotes, right? So this is a left paren, and this is a right paren, right? And we also have a terminal that we care about called a space character, right? So a character is defined as the negative or the negation of anything that is not these 3, right? And then a pair is the more interesting one. And this is where we're going to spend our time really trying to dig into how it is that a pair can be defined in the way that it is. So a pair is made up of a left paren, followed by a node. Notice this is a non-terminal whose definition was up here. We're going to come back to this, followed by a space, followed by another node, followed by a closing parenthesis. So let's imagine this input string down here below, but let's focus on just some simple instances of it. So if we were to ask ourselves, what is, if our input string was just the single letter B, what would we have based on this grammar? Well, if a node can be a char, then a char is any character except those 3. So it seems like this would be a char, right? And if we had C, we would know that that's also a char. But what if we surrounded these in parentheses and added a space between them? Well, then when we say, okay, well, we're looking for a node, what are we going to have next? Are we going to have a char or a pair? So we look at the very first token that we see, right? And that token is an open parenthesis. So we know we don't have a char. And it turns out the definition of pair does begin with an open parenthesis. So we have an open parenthesis followed by something that must be a node. Well, B is a char node, right? So a node can either be a char or a pair. So B is a char node, followed by a space, followed by another node. C was a char node, followed by a closing parenthesis. And it seems like that checks out, right? Well, if we expand this just one more time, we're going to get to the really exciting application of a grammar like this that gives us some abilities that are different from those regular expressions we looked at previously for the purposes of tokenization and scanning. So A is a character, right? We can convince ourselves of that. And if we were to take this full input string, which is now what we have at the bottom of the slide, we have an L paren, followed by a char node, followed by a space. So we're following through on this pair rule. And what we learned in the previous example was that this did make up a pair, right? A pair that was made up of 2 chars. Right? And so when we get to the point of asking, okay, well, let's go parse a node. How do we know if a node is here? Well, we go back to our rule that describes a node, and it can either be a char or a pair. Well, we have an opening parenthesis here, so it must be a pair, right? And we convinced ourselves that this was indeed a pair before. And so notice that we have this structure that has emerged here where this whole input here would be a pair where we have the character A, and on the right-hand side of this pair is another pair where we have a character that is B and a character that is C. And so notice that we've got this structure that we're deriving based on this grammar. Now you might be wondering, well, how is this really different from, say, the regular expressions we looked at earlier? Well, the key difference is a relaxation of a rule that we had mentioned with regular definitions, right? So there's a rule with regular definitions that said you can't reference some rule that was defined that is defined after you, right? So with a regular definition, we couldn't have said a node is a care or a pair. We would have needed to define that after the fact, right? But notice we have a problem. Even if we defined this after the fact, that would mean that pair was then defined based on a rule that came after it, right? So there's this circularity here, or it's actually better to think of it as recursion, right? So a node can be a pair, and a pair is made up of two nodes, right? So a pair can be made up of more pairs, and we could have any number of pairs, as long as ultimately, at the end of the day, notice that this care rule is not recursive. A care rule is effectively going to bring us to the end, or the leaves of our tree that we're going to be deriving here, right? So this is a hand-waving, just conceptual preview of the process of parsing. We're going to need to write some code and produce a body of code that can carry out this same type of process, right? But before we do, let's try and break down the sequence of steps that we're going to need to follow first, all right? So if we want to turn this parsing problem into a sequence of steps that we could imagine implementing in code, let's try breaking it down a little bit into a pipeline. We've previously looked at scanning, and scanning is this idea that given a regular definition of our lexemes, right, we can produce tokens. And scanning is going to read through a sequence of characters one by one with one level of peek ahead and produce tokens, right? That our tokens are going to have not only the actual lexemes themselves, but also the type of token they are. Now, this is going to be something that the parser makes use of. So the parser is actually going to think in terms of tokens, not in terms of the input string. This is something that allows us to differentiate these two problems from one another, to separate the problem of how do we break up our input string into lexemes and put some named types on those lexemes in terms of a token. And then parsing is how do we actually derive the structure from these tokens or these non-terminals that make up our language. And the result of parsing is going to be a data structure that is a parse tree. So in our simple implementation of CharPairs, we're going to have two types of nodes that make up our parse tree. We're going to have pair nodes that are pointers to two other nodes, right? And in this example, if we were imagining this input string here, this would be a pair of the char A and the char B nodes, right? So each of these would be different nodes. And notice that we are losing some of the syntactical structure of our input, right? So we're losing the L paren, the space, the R paren. We're focused now, when we get past parsing, only on what are the actual ideas, what are the ideas that we're trying to express in this grammar, rather than what is the syntax that was needed to get us to that point, right? So we're really trying to make some structure between nested pairs of either pairs or chars, right? And ultimately, we're going to be able to take this tree data structure that we build up from our input in parsing and produce some other output from it, or act on it further. And the output that we're going to produce today is going to look like this, right? So it's just going to be a textual-based output where each time we have a pair, whatever the left side and the right side of that pair are, they're going to be indented on new lines on their own, right? So if we had nested pairs, we could imagine this being multiple levels of indentation deep, right? So very simple output. So let's imagine this. If we've got an input string that does have some nesting in it, so A followed by a pair of B and C, how can we take this and think about what is it that parsing is doing? Well, again, our sequence of tokens hopefully feels pretty straightforward. We've got a left paren followed by the character A space, left paren, character B space, character C, so on and so forth. The grammar that we saw previously can be expressed a little bit more succinctly, as we're seeing here. We've got a node that can either be a char or a pair, and then a char is not any of those tokens that are L paren space or R paren, right? And then the pairs are going to be made up of a specific sequence of expected tokens, right? And ultimately, this is going to produce that parse tree, right? And so here we see another example of a slightly more elaborate parse tree, but notice that a pair can contain a pair as one of its two children, right? And so here we can see that this could be expanded even further. as long as ultimately we wind up finding that the pair has each pair is going to be made up of either two chars or some other pair, we'll be just fine. I want us to talk briefly about a grammar's suitability for parsing, because we're looking at a very simple grammar here that is intentionally designed for being easy and straightforward to parse. Not all grammars are going to be this straightforward. And you can imagine the idea of an ambiguous grammar where the same input string might result in different parse trees, right? The way that we interpret this grammar results in different structures being produced. And if that's the case, if there are ambiguities in the grammar, some of the techniques that we're going to look at today for how to implement a parser for a grammar wouldn't hold up. We would need to refactor our grammar or rewrite our grammar to try and remove those ambiguities from it. The amount of look ahead that we need in order to know what rule are we going to apply next is also something that is informed by the grammar. And we're going to specifically choose grammars that only require us to look one token ahead. A quick example of that here is in our grammar here. If we're trying to figure out, well, we needed to make a node from this rule. How do we know whether we're trying to get a char out of this node or a pair out of this node? Well, we look ahead one character and we see if it's a parenthesis, we know it's going to be a pair. If it's not a parenthesis, open parenthesis, then it's going to be a char. And if it's one of closing parenthesis or a space, we know we've got some kind of error, right? We only need to look ahead one token in order to know which rule to apply next. And so this is the idea of look ahead. How far do we have to look ahead into our input? There are some grammars that you would have to look ahead many tokens in order to know which rule you're going to apply next. And you could rewrite those grammars to be a little bit more easy to parse, but our strategies for implementing a parser wouldn't support that type of a model. The way that we organize our recursive production rules is also going to wind up being important in terms of how easy it is to produce a parser from a given grammar. All of these three things you'll learn in a compilers class are features of a grammar that can be massaged and rewritten. You can express the same language in two different grammar definitions by rewriting your grammars in specific ways that make it more suitable for parsing. So just like you can refactor a program, you can refactor a grammar to try and reduce some of these ambiguities based on the specification of it. But that idea, that concept of how do we actually take a grammar and rewrite it to have different properties is being left to an upper division course on compilers and beyond the scope of our course. So what we're going to be looking at in this course are unambiguous grammars that require only one token of look ahead and won't have any what we call left recursive production rules. This means the leftmost token or the leftmost symbol in a given definition won't be one that's recursive, right? So in this example, notice that if we didn't have an open parenthesis here, if we started with a null, that would not be true because, if we started with node, that would not be true because node is a recursive definition. If we didn't have an open parenthesis here, we would need to do a lot more work to figure out, well, what is it that actually comes next? And it wouldn't be so clear, right? There are ways of addressing that, but we're not going to look at them. We're going to assume that the leftmost symbol in any given production rule is not defined recursively, right? So these three features are what make up a special class of grammars known as LL1 grammars that were discovered and explored in the late 60s, right? And so the LL stands for we're going to work from left to right with the leftmost derivation. Again, these are some technical terms that are being left to the compilers class. And then the one is we're only going to have one look ahead token required. If a grammar satisfies LL1 conditions, it's suitable for a certain type of parser to be able to work with it, called a top-down or a recursive descent parser. So if you're imagining, well, how would I implement this? Am I thinking about producing my parse tree from the bottom up, so starting from my leaves and trying to figure out, well, how would I build up from there? Or would I start from my topmost production rule and try and work in a top-down fashion? Both are possible, right? So both are completely valid ways of approaching a given parsing problem. If you are implementing a parser by hand, and by that I mean you don't have some other program that's implementing the parser for you, then writing a top-down parser that uses recursive descent is typical and expected. It's pretty cool because when you have an LL1 grammar, there's effectively a one-to-one translation between that grammar and the rules of it and the code that you're going to implement. And we'll get a look at that today. And there's this really beautiful connection that I think is somewhat profound and mind-blowing in recognizing that, hey, I can take this grammar and turn it into code and produce these parse tree data structures in a really pretty straightforward way. And it's this really nice connection between the theory of computation and also the underlying systems, such as having a recursive stack or a stack that can support recursive function calls. And it's just really this beautiful connection that hopefully you'll get a feel for today. Now, many programming languages that have much larger grammars or grammars that are better specified, not necessarily constrained to the rules that we're going to be following in this class, they'll use something called a parser generator, where they'll specify in a special purpose language this grammar, and then a program will take that grammar and then generate the code for a parser for them. And that step will produce a bottom-up parser typically. The problem with a bottom-up parser is that it winds up being really, really difficult for humans to reason about and correctly implement when you're doing it manually. There are some rules that you could follow to do this. Of course you can, because if a computer can do it, so could you. But it's much more tedious and would require a lot more effort than doing a top-down parser by hand. You might be wondering, well, why wouldn't a parser generator just do a top-down parser? Well, bottoms up, and what you can do with what's called a Lalor1 parser is allows you to handle a wider range of grammars and can be more performant because it doesn't rely quite as much on recursion. Right? But again, that's a trade-off that's being made mostly